Hi everybody, this is the last section to chapter 4. It's section 4.6, and we're going to look at different properties of isosceles, equilateral, and right triangles in this last section of chapter 4. So in section 4.1, when we talked about isosceles triangles, remember isosceles triangles have at least 2 equal sides, and then a triangle with 3 equal sides is an equilateral triangle. And what we're going to do is just look at different properties of those triangles today. Okay, so remember, an isosceles triangle has exactly 2 congruent sides, and those 2 sides are called legs. So if you see in red here, these are our legs. There are 2 congruent sides. And then we have the third side, the side in blue, is our base. And it is right here. The base of the triangle is right here where it says base. There is a vertex angle. The vertex angle is made up of the 2 legs. And then you have 2 base angles, which are made up of a leg and the base. So again, they're attached to the base, and one side is the leg. Next, we're going to look at a couple different theorems for isosceles triangles. And the first theorem is the isosceles base angles theorem, and that says if 2 sides of a triangle are congruent, then the angles opposite those sides are congruent. So that means if you have an isosceles triangle and you know 2 sides are congruent, then those 2 base angles, as we called them before, are always going to be congruent. All right, so here we have an isosceles triangle, and I know it's isosceles because we have the 2 congruent sides marked there. Now, they want us to find the values of x and y. And because this is an isosceles triangle and these are my legs here, that means that the 58, this is my vertex angle. So B and C, angles B and C, will be my base angles. And I know my base angles are always congruent. So what I'm going to do to find x and y, because they're going to be the same value, is I'm going to take 180, subtract 58, I'm going to get 122 degrees, but I need both angles, and that's the 2 angles together. So I'm going to take 122, divide it by 2, and each angle for x and y will equal 61 degrees. All right, our next theorem is the perpendicular bisector of the base of an isosceles triangle. And this one says if a line bisects the vertex angle of an isosceles triangle. So basically you have a line right here that is bisecting that vertex angle. Then the line is also perpendicular to the base. So it is perpendicular to the base, and it's going to bisect the base as well. So it's perpendicular, and it cuts the base into 2 equal parts because it's a perpendicular bisector of the base. All right, so here we have 2 triangles, and they want us to find the value of x. Now, if I look at the triangles, actually I have 3 triangles here. If I look at just the larger triangle right here, I know that this triangle is going to be an isosceles triangle because you have the 2 sides that are equal. So that tells me that even though I have this segment here, BD, that if A is 51 degrees, then C, angle C, is also 51 degrees. So then I can use that to find not these 2 smaller angles, but this whole angle, angle ABC. And I know angle ABC, if I know the 2 base angles are 51, that is, if I double 51, you get 102. So if I take 180 and subtract 102, you are going to get 78 degrees. All right, so my angle ABC is 78 degrees. Now, we do have BD here, which does bisect that angle. So what I need to do to find x is take my 78 and just divide it by 2. So I know that 2 goes into 7 3 times, and 2 goes into 18 9 times. So x is going to be 39 degrees. All right, next we have another corollary. And this one says, if we know a triangle is equilateral, then it is also equiangular. So if we know all 3 sides are the same, then all 3 angles must also be the same. So that is for an equilateral triangle. And here we have the converse to that, and that is if a triangle is equiangular, then the triangle is also equilateral. So if we know all 3 angles are the same, then we know all 3 sides are the same as well. All right, so here we have a floor plan or floor pattern that's shown, and it's an equilateral triangle. So they want us to find the measure of each angle in our equilateral triangle. Now, if you have an equilateral triangle, we do know that all 3 angles in an equilateral triangle are always equal. So I can take 180, divide it by 3, and we should end up with 60 degrees. Each angle would be 60 degrees in an equilateral triangle. And if you have an equilateral triangle, every time the angles are going to equal 60 degrees, because 3 times 60 is always 180. All right, next we have a theorem that deals with right triangles. And this is your hypotenuse leg theorem, or when you're writing it out, you can abbreviate and do HL theorem. And what this theorem says is, if you have a right triangle and the hypotenuse and the leg of one right triangle, so again, your hypotenuse, remember, if you have a right triangle, just as a reminder, your hypotenuse is always the side opposite that 90 degrees. And then your legs are the 2 sides that make up the 90-degree angle. So if we know the hypotenuse and a leg of one right triangle are congruent to the hypotenuse and a leg of another right triangle, then those 2 triangles are congruent. Now with the HL theorem, you can only use it when you have right triangles. It won't work with any other types of triangles. And again, here's just a reminder for using the HL theorem. You have to have 2 right triangles, so they have to be right triangles. They have to have congruent hypotenuses and a pair of congruent legs. All right, the last thing we're going to do for this section is we are going to do a proof, and potentially we are going to use our HL theorem. So let me write my statements. And my reasons. All right. Let's see here. We're going to start off with our first statement, and it is segment BE bisects AD at C. So it bisects segment AD at C. All right. By now, I want you to be thinking. Okay, that's our first given. What does it mean if we have a segment that bisects another segment at a point? So if we highlight here, so segment BE, so this line right here, is going to bisect, so it bisects AD at point C, so right here. And I'm going to erase that part because we don't really need that part. But if AD is bisected, that means it's cut into 2 equal parts, so that I know that segment AC is congruent to segment DC. I'm trying to keep the order in the same. And that is just simply your definition of a segment bisector or a bisector. Okay. All right. Now, Let's see. I don't have any more information from that given, but I do know segment AB is congruent to segment DE, and that is just a given. And there, it's marked on here already. I really can't get any more information from that, but I have one more given, and this tells me that AB, segment AB, is perpendicular to BC, segment BC, and I also know that segment DE is perpendicular to EC. And I want you to think, when you have perpendicular lines, what do they form? You should say, if you have perpendicular lines, they form right angles. And because we know that AB is perpendicular to BC, there's my first right angle, and DE is perpendicular to EC, there's my second right angle. So I can say that angle B and angle E are right angles. Now, and that's our definition of perpendicular lines. I just use the symbol for perpendicular. Okay. Now, typically when we write their right angles, we want to say they're congruent. But for using our HL theorem here, we just need to know we have right triangles. We don't care if the right angles are congruent. It's kind of a, we don't need to say they're congruent. We don't need that to prove the triangles are congruent. But we do need it to prove that they are right triangles. So what we're going to say is, because we have those two right angles, my next step is going to be triangle ABC, and I don't need that equal sign there, and triangle, let's see, I did ABC, so we'll do DEC, are, oops, right triangles. And that is just going to be definition of a right triangle. Because we know if there's a right angle in the triangle, it is a right triangle. So now, right now, what I have is, so far, I know that AB is congruent to DE. I also know, excuse me, that I have a right angle here. Okay, so AB and DE are legs. And then I also know that AB, or not AB, but AC and DC, so these two segments right here are congruent to each other. And those are going to be hypotenuses each. So I can prove my triangles are congruent right now using my HL theorem, because I know, I'm going to say triangle ABC is congruent to triangle DEC, and that is going to be the HL theorem. Because I have a leg and hypotenuse in a right triangle that is congruent to a leg and a hypotenuse in the other right triangle. Now, they marked angles 1 and 2 here. We didn't use them. We could have talked about vertical angles, but we didn't go that way. So again, sometimes with proofs, you might get to the same answer but go a different way.